Lists are a special data type for reasons you already know. We can contain many values in a list, and they're ordered sequentially, one after the other. Beyond that, though, they actually have a special representation in memory and live in a different part of memory than we've spent much time discussing, the heap part of memory. So in this lesson, we're going to take a look at how do we diagram with lists and look at how do we evaluate while loops in terms of these memory diagrams as well. We're going to pick up right where the last video left off, which is we have this sum algorithm. It's a very simple algorithm of summing a list of numbers. And I've gone ahead and removed comments from this version of it, but you should keep yours in your example if you followed along with the previous video. So the question is, how do we actually trace this program in a memory diagram? And that's what we're going to do together today. Let's go ahead and get the basis of this set up so that we know what happens in memory when we encounter a list literal, like we're seeing here, and how do we represent that in our diagrams and in our memory space. Okay, so I'm going to start off with a stack in a heap space, right? So our call stack is where we keep track of our function frames and the globals frame. So here's going to be where my stack is and my heap space. Right? So far, the only things we've seen in heap are the definitions of our functions, but soon we're going to see that these lists live there as well. So our stack has a globals frame. And the globals frame is where all the names that are globally available in this module will live. And the first thing that we're going to enter into globals frame, because we don't do anything with a doc string, is we're going to enter the definition of sum algo. So sum algo is the function whose definition is on lines 3 through 11. Right? Great. We then see our very first list literal. So whenever you see a list literal and you need to evaluate it, what happens is a new list is constructed on the heap. So list of integers is how we'll give a sort of a title to this table we're setting up. So we keep track of lists in terms of a table. And it has a single element. It has the element 110 in it, right? So that's the element 110 at index 0. Great. The convention we'll use is, the leftmost column of our table when we're working with a list is going to be the index, and then the item associated with that index is the value on the right column. And this is assigned the name single in globals. Now I'm actually going to highlight this arrow and the box around this list to say these are what's really important in this video, recognizing that our list values, the names that we assign to variables that hold are simply values that hold references to the lists which actually live over in the heap. So when we ask ourselves, what is single? What is the word single here that we've just defined as a variable? And when we use it later, what's going to feel kind of nuanced is single is actually the reference to this list. It's not the list itself. Right? And that is a somewhat nuanced distinction that we'll become more comfortable with over the next few weeks. This idea of a reference, and this arrow is a reference, has some deep implications that we need to be careful of, because when we can have multiple references to the same thing, if someone that has that reference changes that value, then everywhere else in our program, we need to be aware that it could have been changed. But for now, just know that this word single, this variable name single, is bound to, with a reference arrow, this list value. I should note that this arrow, where it points to on this list, is insignificant. If it pointed to the bottom of the list or the top of the list, or even oddly, the right-hand side of the list, we mean the same thing for each of those. We're not pointing to something specifically inside of this list. We're pointing just to the idea of this list object that lives in the heap at large. Great. So we then see another list that's set up, a list with many items in it. So this is once again a list literal expression. So whenever we see a list literal expression, we need to set up a list value or a list object on our heap. So this is another list of integers. And this list of integers has the values 1, 3, and 5 at the indices 0, 1, and 2. All right, so let's set up our table. Notice this is a distinct and separate list from the first list we set up. It's totally fine and actually very common to have many different list objects living in a program's memory at the same time. And here that's the case. All right, so we have a variable named mini. And what is mini? Well, mini is also being assigned a reference to, or it refers to, it has an arrow that is going to point to this list object. All right, so now mini refers to the list object whose length is 3 with elements 1, 3, and 5, and single is the variable that refers to the list object with a 1 element whose value is 110. All right, well now we reach sort of the, the fun part of this exercise, which is what do we do with a function call where we're referencing a list, and how do we pass a list as an argument to a function whose parameter expects the same? Well, we move through the exact same set of steps we always would, right? So whenever we reach a function call, we need to carry out the same set of steps to check over our backs and make sure we know what we're doing and that it's a valid function call. So to check this as a valid function call, we ask, have we seen something named sumAlgo before? And is it a function? Yes, sumAlgo is a function defined on lines 3 through 11. So we're talking about this function here. Then we ask, well, do the arguments line up with the parameters? So do we have the same number of them? There's one argument here, there's one parameter. And we ask, well, what is single? Single is a list of integers. Okay, well, x's, which is this parameter, expects a list of integers. So that checks out. It looks like we've got all that we need for a valid function call. So let's set up a frame to call the sumAlgo function. All right, so sumAlgo is a function call that occurred on line 16, right? So the return address is line 16. That's where we're going to go back with our return value once we've figured it out. And we need to pass this x's parameter. So what is x's going to be, right? And here's where these arrows become important, all right? So x's is going to be whatever single is in globals. So single in globals is an arrow to this list where the first item is 110. So x's in sumAlgo is also going to be an arrow. Let me choose a different color here. I'm going to choose pink. I want this to be, a spicy arrow because it's a very important one. This pink arrow is pointing to that exact same list. So notice now single and x's both refer to the same list object on the heap that has one element in it, right? So when we pass an argument whose type is a list, or we'll see this generally applies to many other kinds of types that are reference types. We'll learn more about that in a future lesson. We're going to be making sure that we have an arrow that points to the same place that the original variable's arrow pointed to. So here, x's is referring to that same list as single does in globals. Great. So we're ready to jump into this function. All right, so what do? Well, we jump into the function definition, and there's nothing to do in the doc string. Then we reach line 5, where we set up a total variable. So total is 0, right? And we set up an index variable named I. So I is 0. Great. And then we reach a while loop. When we encounter a while loop, and we're trying to trace the evaluation of a program, we need to be sure that this expression is either true or false. That's going to decide where we go next, right? So what is I? I is 0. 0 less than, what is length of x's? Well, again, we have to think in terms of our current frame. The current frame we're working on is the frame on our stack that's the lowest that hasn't returned, right? So that's this frame here. And in this frame, x's, this pink arrow, refers to the list with a length of 1, right? So 0 less than 1 is what this expression is asking. Is that true or false? That's true, right? So this is true. That means we're going to go into the loop body, or the repeat block, we like to call it. And now we're asking, okay, we've reached our relative reassignment. So this is the same as saying total plus x's index I is being assigned back to total, right? So let's break this down. What is total? Total is currently 0. So 0 plus x's index I. What is index I? 0. So this is 0 plus x's index 0. What is x's index 0? So x's index 0 is we follow this pink arrow, we look up index 0, and it's the value 110, right? So we're saying take 110 and store that in the total variable's new value, right? So I might just cross this out. So total's new value is 110, right? So we've, added the next item, x is at index 0, the very first item of our list, to our total, which was previously 0. Great. Now we need to move to the next index. How do we do that? Well, we increment our index variable I. So I is no longer 0, it's now 1. Right? And then this is what's important. When we reach a while loop, we go back up to the top and we ask, okay, is this expression true or false? We ask this again afresh, like we were asking for the very first time. So I is 1. Length of x's, is this the list this pink arrow refers to. That's also 1. So 1 less than 1. That is now false. Because that's false, we're going to jump over the block of the while loop and we'll hit this return statement. And now we need to evaluate, well, what is total? All right, so total in our current frame is the value 110. So that's our return value. What do we do with this return value? Well, we're sending it back to the return address on line 16. So we're sending it back to where this function call originated. And now we're going to print 110 is the first line of output that would be printed in this program. All right, so simple enough. Summing up a list with only one element in it, no big deal. All right. What I'd like to do next is turn it over to you to try and carry out the full evaluation of this line, printing the result. And actually, let me keep track of my output here for good practice. So output, we just said the printed output was 110, right? But I want you to try carrying out line 17 and adding a frame for that function call, fully evaluating it and convincing yourself that you traced through the while loop successfully. And then we'll do that together after the break. So go ahead and pause the video here. We'll be back in 5 seconds. All right. Hopefully you were able to successfully navigate that. But if not, or if you had some uncertainties, let's walk through it together. For my purposes, I'm going to need to both disappear because I'm covering the list on the right-hand side of my screen, but I'm also going to need to remove this sum algo frame from my diagram. You shouldn't do this. You should leave yours in your diagram, but for purposes of space and being able to fit all of this on my screen, I'm going to remove this frame so that we can evaluate line 17. And maybe I'll just add sort of an intermediary ... here to be sure that you knew that there were things that happened in the evaluation of this that aren't going to be on my screen. Okay. So what did you need to do? Well, hopefully you checked and convinced yourself that this was a valid function call. We've already seen some algo as a function that has a definition. Mini is this reference arrow, this blue arrow that refers to the list of integers. That corresponds just fine to the parameter x's. So this is a valid function call. So let's go ahead and set up our frame. So the frame is for sum algo. And the return address this time around, is one line after the previous call. So this is line 16. All right. And we're going to need to set up our parameter. So x's is the name of the parameter inside of this function call. And here's where we get our spicy arrow, right? We're saying, okay, take mini. What is mini? Mini is, this reference here, and assign that same reference to x's. So x's is also going to refer to that same list, right? So now we've set up our reference for x's, and we are ready to jump into this function definition, right? So we're ready to carry out the body here. So we're gonna set up a variable named total, whose value is 0, starting back from 0. I is our index. That's also going to be 0. And we reach our while loop. So we ask ourselves, is I in our current frame is this one, right? So, we've got now your diagram is going to have, total and I in the previous frame that's already completed. But now we're working in the frame, which is the lowest on our stack that hasn't returned, where total is 0 and I is 0. So is 0 less than the length of x's? Well, now x's refers to this list that has a length of 3. So 0 less than 3, that's going to be true. Great. So that's true. We go into the loop and we once again are asking, okay, total plus x's index I. And so what's total? Total is 0. Add that to x's index I. So x's is this table or this list, and I is 0. So I is 1, or that value is 1, right? So the 0th index is this value here, 1. So 0 plus 1 is 1. We reassign that back to total. So now total's value is updated to 1, right? And for this part of the diagram, I'm just going to erase my numbers, but you're free to scratch yours out and keep a list of all the values you assign to total. But its current value is 1, right? Similarly, we need to increase our index. So the index increases by 1, so the index is 1, right? We reach the end of that while loop. We go back up to the top, and we need to test this condition again. So I is 1. Length of x's is 3. We didn't change. Nothing about that length changed. But notice the index did change, and this is important. If this index wasn't changing, we would have an infinite loop. But we don't, because we're making progress towards this no longer being true, right? So this is true. 1 less than 3 is true. So we go into line 8, and now we ask, okay, well, we need to add total's current value plus x's index I, right? So total's current value is 1. X's index I is the same as x's of index, and then our i's value is currently 1. So what's x's of index 1? Well, we look at x's, and index 1 has a value of 3, right? So 1 plus 3. That's going to be 4. And so 4 is going to be reassigned to total, right? So we update total. So total is now 4. Great. And you know, when you talk through each of these steps and you think through each of these steps at the very detailed way the computer's doing it, it's easy to lose sight of, you know, the bigger picture here. But the bigger picture here is, you know, all we've done is we're summing, you know, 1 plus 3, right? Like we started from 0, we added 1 to 0, then we added 3 to that total, and we're carrying out the same sum algorithm, just step by step in the way that the computer does, right? So now we need to move again to the next index. So we update our index variable to be 2. 1 plus 1 is 2. And we reach the end of our while loop, so we've got to go back up and test this condition, all the new. So I is 2, less than length of x's is still 3. 2 less than 3 is true. So we go into our loop again, right? We haven't finished the job here. So again, total plus x's index I. Total is 4. And we're going to add that to x's index I. Well, x's index I is 2. So this is the same as saying x's index 2. X's index 2, well, here's x's, and index 2 is 5, right? So 4 plus 5 is 9. What are we doing with 9? Well, we're taking 9 and we're reassigning that back to our total, right? We've just added the next item in our list to our total, and total is now 9, right? So we've added that item and we're ready to move on to the next index, right? So we add 1 to I. I's value is now 3, right? We reach the end of our while loop, and now we go back up and we test again. Is 3, which is the next index we would need to add, less than the length? Is it still a valid index is what we're asking here. Well, this length is 3, so this is false, right? And I want to point out that there's this sort of, when you first get used to writing algorithms like this, there's a little bit of discomfort in this idea of, you know, why am I checking this at the very start? Well, one reason is if we had an empty list, you know, and the length of that list was 0 and I is 0, 0 less than 0 is false. So you would never try and add anything together because, you know, with an empty list, the total would be 0. But as we're moving through this, we don't really know ahead of time, and we don't really want to have to write an extra check. Is this the last item? Is this the last item? So what we say is, well, is this just a valid index? Sure. So while that's a valid index, we're just going to start from, you know, index 0 and keep moving our way up one by one by one while it's still valid, and organize our solution in that way, right? So because this was false, that means we're going to jump past the loop and we're ready to evaluate this return statement. So total in our current frame is the value 9. That's our return value for this function call. Once we reach our return statement, the function call's job is done. And now what do we do with this 9 value? Well, we return it back to line 16, where, oops, the return address here should have been 17. That's my bad. This call to sum algo was on line 17, so apologies for that little mistake. And we return line 9 back to line 17. Okay, and this function's job is complete, and the additional output here would have been 9 gets printed, right? And wow, that's a lot of steps to move through just what feels like a very simple summation, right? All we were doing was adding up 1 plus 3 plus 5, but in order to fully evaluate a program like this and to write a program like this, we needed to break those steps down and carry them out piece by piece, one by one. So in this video, you got some practice with the idea of where we're going to place our lists in our memory diagrams. And the important thing to recognize is that lists, when you have a list literal, those list literals will construct new list objects on the heap. Now, what's kind of unique and we'll spend more time getting comfortable with is when you use a list as, say, an argument, you're not copying, you're not making a complete copy of that list. So you now have two lists of the same values, like we were when we had numbers and Booleans as arguments. We're actually giving a reference to the exact same value. Now this algorithm, the sum algorithm, isn't changing anything about those lists, but we'll look at algorithms later which will, and that's going to be part of the motivation for why we want to be very careful about understanding the implications of passing things by reference, which is what we're doing here. Meaning, when we called this sum algo with mini, we copied this reference. And so we're passing this reference in so that now x's and mini refer to the same object. This is a preview of something we will spend much more time on, the difference between values and references, and the importance of that distinction when we're dealing with mutable objects, meaning objects we can change, such as a list where we can change the item's values, we can append to it, we can remove from it. When we combine those two concepts, we have to be very careful about the way we design our functions and the implications of changing our lists in function calls. But that's for another day. For now, if you could follow along with the diagrams we've got here, you're in great shape. So great work on today's lecture, and we'll see you next time.